we doing? All right. How's the weekend? As far as your quiz went on Moodle, I went through and graded the one about the transformations, the list of transformations off, so that should be corrected in there. Also, I realized on one of the answers I didn't give you any correct option on it, so everybody got full credit for that one particular problem. So, anyway, any questions at all over anything before we continue on with our discussion of inverse functions and then move on to quadratic functions today? All right, I want to do one more example that's not in your packet today, but I want to do one more example like that. The problem we did at the end of class last time, where we're asked to find an inverse of a function that is written as a fraction there. So just to do this off to the side, let's say you were asked to, say I suppose I asked you to find the inverse of f of x equals, we'll say 2x minus 1 over 5x plus 6. What do we do first? Yeah, let's switch the x's and y's, right? Remember, we think of our f of x as the y, because our outputs would give us the y coordinates. So our first step here is to change all the y's to x's, which there should only be one of them, and then change all the x's to y's. So doing that in this case, we'll get the equation x equals 2y minus 1 over 5y plus 6. What do we do next? What do we want to do? We need to get y by itself, right? The next step in finding an inverse is to get y all by itself on one side of the equation. To help us out with that, what should we do first? Good, yeah, multiply both sides by the 5y plus 6 to clear that fraction out. So multiplying both sides by the 5y plus 6, we should get x times that 5y plus 6, and then equals 2y minus 1 on the right-hand side. What should we do next then? Yeah, so again, I want to get y on both sides, or excuse me, y on one side, right? Right now I have y on both sides. So I want to gather my y's on one side. To be able to do that, I need to distribute my x through first, right? It's attached to this 5y plus 6. So distribute that through, what do we get? And we still have the 2y minus 1 on the other side. So we distribute our x through, we'll get a 5xy plus 6x on the left-hand side, and a 2y minus 1 on the other side. What should we do now? Okay. Yeah, so you can pick, it doesn't matter which side you pick, I just need to get the y's on the same side and everything else on the other side, right? Doesn't matter which side you do it. We can subtract the 2y over and subtract the 6x over, or you can subtract the 5xy over and add the 1. Either way is fine. You just have to get all your y's on one side. Which would you rather do? Do you want to subtract 2y or do you want to subtract 5xy? Literally does not matter, but yeah, subtract the 2y, okay. You just have to make a choice. So subtract the 2y over to the left-hand side, subtract the 6x over to the right-hand side. We'll get 5xy minus 2y equals negative 6x minus 1. Why did we put all the y's on the same side? What can we do now? Yeah, we can factor the y out. That's exactly what we need to do. Factoring the y out gives us y times the 5x minus 2 in the parentheses, and then equals 6x minus 1. Finally, then, we can divide by that 5x minus 2 to both sides. And this now is our inverse function. Again, the reason why I have you do this type of problem, besides the fact that being able to find an inverse function is an important skill, the idea of being able to gather like terms to one side comes up over and over again. So that's the reason why we're doing this, is I want to gather the like terms to one side so that we can factor off the y's in that case. Questions on that one at all? All right. So let's go on and talk about how we can graph inverse functions given a graph of a function. First, let's remind ourselves, if we look at a graph of a function, how can we tell whether or not it has an inverse function? How can we tell if the inverse function actually exists? What do we do? What test do we use? Horizontal line test, right? Remember, we have to have one-to-one functions in order to have inverses. One-to-one means that if I put different things in, I have to get different things out. Okay? Horizontal line test checks to see whether or not you put two different things in and got the same thing out. So it'd be at the same height, the same y coordinate. Does this graph pass the horizontal line test? Yeah, it sure does, right? So the graph does represent a one-to-one function. So we do have an inverse. If we were finding the inverse algebraically again, we would invert or flip-flop our x's and y's. And then solve for y. So we can subtract 1 from both sides and then divide by 4. So our inverse function would again be a line. What would the slope here be? 1/4, right? The y-intercept would be also negative 1/4 in this case, right? So if we were to graph this, our y-intercept is negative 1/4. And if you go right 4, you would go up 1, down 1, sorry. It's a negative, or sorry, let's put a positive 1. If I could figure out what my slope is. All right. So you're going to get a line that looks like this, roughly. So this was the graph of f of x equals 4x plus 1. This is the graph of the inverse function, which is 1/4 x minus 1. One thing that we notice, or hopefully that we notice, is that we have a little bit of symmetry going on in this graph. In particular, if I draw in this diagonal line, the original graph and the graph we just drew should look like a mirror image across that line. The reason for that is because remember how we figured out our inverse function, right? So for example, what are the coordinates of this point right here that I just put in red? This one right here. That coordinates of this red point right here, what are the coordinates? 0, 1, right? This one right over here, 1, 0. Notice I got flip-flopped around, right? Okay. Or if I put in, let's say if we put in 1, up here we would get 5. This is the point 1, 5. Whoa, hey. Notice over here we would have the point 5, 1. Notice that your x's and your y's get flipped around. Right? So the way that we can get if we just had the graph and wanted to get a graph of the inverse, the way we can get a graph, we start with the y equals f of x, and we reflect the graph about the line y equals x. So I'll go back up to the graph here in a second. But the idea, again, for your inverses is that you're changing the x's and the y's. You're flipping them around, right? You're flip-flopping the roles of the x and y. So if I reflect them around the line, y equals x, that's exactly what happens. If I have x, y over here, I flip it around, and I get y, x over here. So again, our inverses are exchanging the roles of x and y. They interchange the roles of x and y. So if you start with a graph, you can get the graph of the inverse just by flip-flopping it around that line y equals x, which is that diagonal line that we drew in here. Notice for lines, this kind of makes sense as far as the slope, right? Remember, your slope is change in y over change in x. If you flip-flop your x's and y's, you get change in x over change in y. It would reciprocate your slope, which is exactly what it did, right? If you're flip-flopping what x and y means, you're interchanging their roles. It makes sense that you would get the reciprocal there for the slope. All right. So let's see if we consider that idea here. You don't have to draw this first graph in, but if you were to take this particular graph, I wouldn't draw it right now, as a matter of fact. If we were to take this first graph and flip it over the line y equals x, you would get something that looks like that. We take it and flip it basically on a 45-degree angle, if you will, right? This thing would flip this way. What's wrong with this red graph? Is that a function? No. Notice that your original graph did not pass the horizontal line test, right? So when we do that flipping across the line y equals x, our red graph is not a function. Makes sense, right? We said in order to make the function an inverse, in order for a function to have an inverse, it needs to pass that horizontal line test. It needs to be 1-to-1. The problem with this particular function is that it's not 1-to-1, right? Can you tell me two different numbers to plug in for x that give 1 out as an output? -1 and 1 will both work, right? So there's two different outputs that give me the same, try that again. Two different inputs that give me the same output. So it's not 1-to-1, right? So that's what goes wrong here when we graph this particular function. If I just blindly try to do this reflection around the line y equals x, I get this parabola, this U-shaped thing, and it flips on its side. Right. So this function itself does not have an inverse. However, when you do squaring functions, there's a lot of times that you want to undo squaring. What do you do to undo a square? Take a square root, right? So we usually think of square rooting as the inverse of x squared. But we just said that the function f of x equals x squared on its entire domain does not have an inverse that's a function. Okay? So think about it again. When you do the square root function, do you ever get a negative out of the square root function? No, you get always a positive out of the square root, right? We refer to that as the principal square root. Okay? The way we get around to this issue of not having an inverse over the entire domain is to restrict it. So for the squaring function, we restrict our domain to just the positive side. Okay? We restrict f of x equals x squared to the interval 0 to infinity. And we ignore the left-hand side. Notice that when we do this restriction, I want to restrict it to take up the entire range of the function. I want to be able to, when I do the inverse, I want to be able to look at the entire range. I want to undo the entire range. There's two ways I can do that easily. for x squared. I could do the negative side, or I could do the positive side, right? I could have chosen the left graph, the left side of the graph, or the right side. And I do mean a choice. We literally are choosing the positive side. Just the convention that we use. We could have just as easily picked the other side. So be mindful of that. It's also when you pops up again when you solve equations. If you do the square root of both sides to get both the solutions, you always do plus or minus because of that. Yeah. All right. So we restrict to 0 to infinity. Again, to make sure that we take up the entire range of the function. I want to be able to undo all of the values that are in the range. I want to be able to undo all the outputs and find an input that corresponds to them. Okay? So again, I could have restricted a little bit. That makes a one-to-one function, but I can't undo then all those points that are above that, which is not very interesting. So when we do the restriction, we always want to make sure we hit the entire range so that I can undo all of them. Now notice that when we do that reflection about the line y equals x, we do get a function now, right? And this is your square root function. All right. We have to restrict the domain for functions that aren't one-to-one if we want to talk about inverses of those functions. The square root function is probably your first example of such a function that you would want to be able to undo. You would also need to do the same things if you want to do a fourth root or a sixth root or those kinds of things. All right. So let's look at this next example. It says, using an appropriate domain restriction, find the inverse. Notice again, we have a squaring function. We're going to talk a little bit more about what these graphs look like in the next section. But we have a squaring function here. Anytime we have a squaring function, then we know that if we put in a positive or the negative, we'll get the same output, right? If we put in a positive one or a negative one, when we square it, the negative goes away. Okay? So we know that those are not one-to-one. So let's see what would have to happen here in order to get this domain restriction that we're talking about. So let's just say we started, let me change back to black here. Let's say we just started this problem the same way we have been. Again, first step would be to do what? Good. Change the x and the y. Good. So we have x equals 3 times y plus 4 squared minus a 5. And now, again, our goal is to try to solve for y, isolate the y, right? What do we need to do first to do that? Eventually, I'm going to have to get rid of the square, right? So let's isolate the square first. To isolate the square, what do we need to do? Yeah, add the 5 to both sides. And then divide by 3. Good. So far, so good. This is not any different than any of the other problems we've been doing, right, for solving finding inverses. The next step would be to undo the square, and this is where the issue comes in, right? When I undo the square, I don't know if I'm on the positive side or I'm on the negative side, right? So ordinarily, you don't have to write this part down. I'll erase it here in a second. But ordinarily, if you were to do the square root of both sides, at this point you would write plus or minus square root of x plus 5 over 3, right? All right? Okay? We would, when we do the square root, I'd have a positive or a negative. How would I decide which one is which? in that case? Well, let's go back up to that squaring function. Notice going back over here, we restricted our domain here to the positive ones and ignored the negative ones, right? And we made our domain restriction go 0 to infinity. Well, going back to, let's think about transformation stuff as we go through here. If I have a plus 4, if I had a y plus 4 or an x plus 4, I'll think about it as x's. If you did x plus 4 quantity squared, what would that do to the graph of x squared? Move to the left by 4, right? It would shift it over to the left by 4. So going back up to my graph of x squared, if we shifted left 4, it would have the exact same shape. We would just be shifting it to the left. So what do you think you would restrict your domain to in that case? Instead of going 0 to infinity, what would you just restrict to? Negative 4 to infinity, right? Because we moved to the left, right? So if at this point we restrict to 4 to infinity, or negative 4 to infinity, I don't need to worry about the plus or minus. It has to be the positive. So we're in this particular problem, we're going to restrict to negative 4 to infinity, or better said, probably x is greater than or equal to negative 4. And then finally, we can subtract our 4 to the other side, and then this would be our inverse function. Thinking about it another way, if we go back up to the original problem, notice that if we put in negative 4 for x, that makes that inside 0, right? That's where it's going to bottom out. So we want to restrict to the positive side to get an inverse function here. Or you could also restrict it to the negative side. You've got to restrict it somewhere. So in this case, we would restrict it to negative 4 to infinity. Make sure that we're only getting positive values inside that squaring so that when I take the square root, I can use the positive square root. If we instead restricted it to negative infinity up to negative 4, instead of using the positive square root, we would have used what? Negative square root. Okay? And again, if you think about what the graph of the function looks like, it's that U shape, right? So either we're using the right-hand side or the left-hand side, one or the other. The moral of the story here is that you have to, if you want to invert functions that aren't one-to-one, you need to pick an appropriate domain restriction. The best examples we have right now are squaring functions, where we want to do the positive square root versus the negative square root. But if you go on to, say, trigonometry, you get all sorts of functions there that are not one-to-one, and you have to pick an appropriate domain restriction, which I'm actually talking about today in script class when I go teach that in the next hour. All right. Any questions on that at all? Is our process with solving for inverse functions okay? All right. Let's talk a little bit about properties on the next page here. Remember again, the whole point of inverses is to undo your functions. Whatever the original function did, you want to do it in reverse, right? You want to undo it. Graphically, and how we solve for them. Remember again, we interchange our roles of x and y. So if we're going to interchange roles of x and y, what do you think the domain of the original function becomes? If we're going to interchange what x's and y's are between original function and inverse function, the domain of the original becomes what for the inverse, do you think? Well, what does domain refer to, x or y? X's. If we're going to interchange x's and y's, the domain of the original becomes the y, the range, right? It becomes the range for the inverse, right? What do you think about the range for the original? What do you think it becomes? The domain, exactly right. So if we have a domain of the set A for the original, the range is going to be A for the inverse. If you have a range of B for the original, then the domain becomes B for the inverse. Let's go back up to the previous example and see what we mean here. The base graph, if we think about the graph here, the base graph would have been x squared. We would have shifted it left 4, stretched it by a factor of 3 vertically, and then down 5, right? In particular, I'm not going to really draw this to scale. I'm just going to put the bottom where it should have been. The bottom should be here at -4, -5. That's left 4 and down 5, right? Then your graph would have gone this way, roughly. I didn't scale it vertically right, but that's what it should have looked like, right? The bottom should have gone left to the 4 and down to 5, -5. Left to -4, down to -5. If we restrict the domain, that's the part of the graph we're looking at, right? We agree with that? So the domain of the original was -4 to infinity. That's what we already said we were going to restrict the domain to. What's the range looking at that? We said the bottom went left 4 and down 5. So what's the range going to be? Good, -5 to infinity, right? It bottoms out at -5 and goes up, doesn't it? We found and this was for the original function, right? Let's look at your inverse function. We just said the domain for the original turns into what? The range. So here the range should be -4 to infinity. Well, let's see if that makes sense. What would be your base graph here? What would be your base function if you were doing this with transformations? Be square root, right? Where does your square root function bottom out at? What's the lowest thing that you can get out of a square root function? What does your square root function look like originally? Like that, right? Where's that bottom point? It's at 0, 0, isn't it, right? So the lowest thing you can get out of 0, what is this -4 out in front here telling you you're going to do? It's going to go down 4. Isn't that what happened to the range? It went down 4. Instead of being 0 to infinity, it went -4 to infinity. Looking at your original graph again, your range is -5 to infinity. What does that change to for your inverse? The domain. Does that make sense for what we came up with the function here? What can go wrong with square roots? Negatives, right? What do you need then to be true for the underneath that radical? We need that x plus 5 to be greater than or equal to 0, or x is greater than or equal to -5. So notice that property we just talked about a minute ago matches up with exactly what we would have had with this previous example, right? The domain of the original became the range for the inverse. The range for the original becomes the domain for the inverse. They flip-flop. Which makes sense because, again, inverses interchange the roles of x and y. Right? So they need to flip-flop. All right. Let's talk about some other properties. The whole point, again, of inverses is that they're supposed to undo each other. So what that means is if I square something and then square root it, that should cancel each other out. I get back to where I started, right? That's what that means, right? Okay. If I cube something, I would need to cube root it to get back where I started, right? So what these properties here say, if I do the function and then undo the function, where should I end up? This is composition, right? F inverse of f of x. If I do the function and then undo it, where should I end up? Where I started, right? What did we start with? X. So we started with x, we should end with x, all right? This should be x. Change back to black. Should we end up back at x? This is saying the exact same thing, just in the reverse order, right? So if I do the inverse function and then do the original function, what should I end up with? X again, yeah. All this is saying is that inverses undo each other. If I start with x, plug in into the original, and then undo it, I should end up back at x again. If I start with a bare foot, put on a sock, and take off my sock, I'm back to a bare foot again. Right? Same idea. Okay? Now, what I do have to be is careful, because again, some of these inverse functions are defined by domain restrictions, right? What do I mean by that? If I do the square root of 2 squared, I get 2. So I did get back to where I started, right? I squared the 2 and then undid it by undoing the square root. But if I start with -2, did I get back to where I started? No. -2 wasn't in my domain restriction, right? I have to be careful. Okay? I got to make sure that what I plug in is in my domain and in my range appropriately. All right? So this first part is provided that your x is in the domain of f. And the second part is provided that your x is in the range of f. Remember, this x has to come out of, at the end here, the inverse function, right? Remember your range of your inverse, that would be the set of outputs for your inverse, that's equal to the domain of the original, right? So this undoing property only works if I can plug my x into the f to start with, or it's in my domain restriction to start with. When I flip them around, my x has to be able to come out, be in the range of the original, because it has to go into the inverse function. It has to be in the domain of the inverse. So I have to be a little bit careful. And again, this is our prototypical example of when we have to be careful. The square root undoes squaring if what you're squaring is positive. Okay? The square root does not undo squaring if you're squaring a negative. Technically, when you do the square root of x squared, you get absolute value of x because it removes the negative sign. You have to be a little bit careful. All right, well, let's see if we can put these properties to use real quick. If I start with a 1-to-1 function, when I plug in 5, I get out -2. If I take an input of 5 and get an output of 2 for the original, what should happen on the inverse when we plug in a -2? What should we get out? 5. They were, again, remember, inverses interchange x and y. This is my x, this is my y. For my original function, they flip-flop in the inverse. What about the next one? If f inverse of 3 is 6, what's f of 6 going to be? 3. Again, they reverse them, right? Doesn't matter the order. This is input for the inverse is output for the original. Output for the inverse is the input for the original. So they just flip-flop. that okay? We're just recognizing that they're interchanging, right? Okay. So the next one's a little bit more involved, but not too bad. They give you a function, f of x equals 3x minus 2, and you want to plug 7 as an input into the original, right? Or sorry, 7 as an input into the inverse. Sorry about that. They give you the original function and it says, what happens when you plug in 7 into the inverse? Okay. So it's an input for the original, means it has to be what? It's an input for the inverse. What does it have to be for the original? An output, right? So if I want to figure out what this answer is, what do you think we should do? If that 7 needs to be an output for the original function, what do you think we should do? Good, exactly right. This needs to be an output for f of x, so I'm going to set that f of x equal to 7. I want to find the input that corresponds. That's what the inverse function says. All right? So we'll have 3x minus 2 equals 7. So what does x have to be? 3. And so that would be our answer here. This is just a fancy way to say, what do I need to plug in to get 7 out? That's all it's asking you to do. Questions on that one? All right. This last one is asking us to show that they are inverses of each other. So we want, what this is asking us to do is show that they really do undo each other. So what it's asking you to do is compose the two functions and see that they really do undo each other. Now we just said a little bit ago, if they're inverses, when they undo each other, I should get back to where I started when I do the composition. We just said that a little bit ago, right? So that's what all this problem is asking you to do, is do the composition and see that you get back x out. So let's do the first one, then I'll leave the second part for you to practice because it's similar. What is this? If I want to do f of g of x, what do we do first? Yeah, we replace the g of x with what it is, right? So it wants us to do f of 1 over x plus 2 minus a 1. And then what do we do with this? Yeah, plug it in for the x into f of x, all right? Oops. Oh, I forgot plus 1. That was what my problem was. My x is getting replaced with 1 over x plus 2 minus 1, right? So I just put parentheses around it to emphasize that. We took out this little x here and replaced it with this whole big thing here. What do you notice happens on bottom? Yeah, the 1s and the minus 1s cancel each other out, don't they? Okay, so we have 1 over x plus 2 minus 2. What is 1 over x plus 2 equal to? Ask a different question. What's 1 over a half equal to? Not a trick question. What's it equal to? It's equal to 2, right? I'm just reciprocating the reciprocal, right? I flipped it over and flipped it back. So what's 1 over x plus 2 equal to? X plus 2. And I still have that minus 2 on the end, so what do we end up with? X, yeah. Which is what we're supposed to end up with if they're inverses of each other. Another way to think about this, of course, is that when you divide by a fraction, what do you really do? Multiply by the reciprocal, right? So this would be 1 over x over 2 plus, or 1 times x plus 2 over 1. That's why we just get x plus 2. Well, again, we're just reciprocating a reciprocal. That's all we're doing there. Right. I'll leave the second part for you to do the inverse, the composition in the other order. Are there any questions about this at all? Before we get started on some new stuff, other stuff. Gosh, I can't talk today. This okay? This is a good review of composition, which is why I'm leaving that second part for practice for you. All right. Let's talk about, start the next section, and we'll go through it on Wednesday as well. What we're going to do in this next chapter is start looking at specific types of functions. In particular, we're going to look at polynomial functions. The first one we're going to talk about was referred to as quadratic functions. We've already played around with these a little bit. We're going to get some special properties and solve some application problems as we go. Oops, sorry. I always do that. Sorry about that. All right, so let's look at what we mean by a quadratic function. Well, we've already talked about our catalog of functions that we started with. One of those types of functions that we started with is f of x equals x squared is our base graph. That's exactly what the quadratic function idea comes from, is that using that x squared as a base graph, we just may have it moved around a little bit. So we refer to something as a quadratic function if f of x can be written in a form f of x equals ax squared plus bx plus c with a not equal to 0. Why do we make sure that a is not equal to 0? If a is equal to 0, what kind of function do we really have? If the a is equal to 0, what kind of function do you really have? If a is equal to 0, what happens to the first term? It cancels out. What are you left with? A line, right? It's a bx plus c. That would be a linear function, right? We've talked about linear functions before. It was on the last test, as a matter of fact, right? Okay. This is why we say that the a needs to be not 0, because I really do want the x squared piece to be there. Okay. And I've already talked about this a little bit earlier in the semester. The highest power of x that you see is the one that dominates the function. That one kind of tells you what kind of function it is. What does x squared look like? What does the graph look like? Yeah, the U shape up, right? And we call that type of shape parabola. That's exactly what the graph of a quadratic function is called. It's called a parabola. And in general, there's two basic shapes of the graph. It's going to go maybe up, or it could go down, right? Those are your two basic shapes. What was going to tell you whether it goes up or down, do you think? Yeah, exactly right. If it's a positive x squared, we know the graph looks like this. If it's a negative x squared, what does the negative on the x squared tell you to do? It tells you to flip it which way? Up across the x-axis, right? Flip it upside down, right? Okay. So you're going to get a graph that looks like this one as if your a is positive. You're going to get a graph that looks like this one if your a is negative. Now, one of the important things that you might want to know about a parabola, about the graph of a quadratic function, is this point where it bottoms out or the point where it tops out. If we think about it from the original graph, if I do f of x equals x squared, where does that thing bottom out at? 0, 0, right? We refer to that place as the vertex, by the way, where it tops out and bottoms out. It's called the vertex of the parabola. One of the things that might be very, very helpful to us is to figure out where that vertex ends up. Right? If in particular for models, the bottom out spot would be a minimum. The top out spot would be a maximum, right? So the vertex is going to give us a maximum or a minimum depending on the situation. We're going to talk about that on Wednesday. But it might be helpful to know where that vertex ends up. Think about your transformations. If I multiply by a constant outside the squaring or inside the squaring, is that going to change where the vertex goes? If I do a stretch or a compression, either vertically or horizontally, does that change the vertex? No. The only thing that's going to change it is left, right, up, down, right? So that's what the standard form is going to help us with for a quadratic function. We can, within standard form, we write it as f of x equals same a, but we might shift it left or right, might shift it up or down. Okay? So this is what we refer to as standard form for a quadratic function. If h is positive, then I'm doing x minus something, so it goes right. If h is negative, then we're doing x plus something, it goes left. Right? It does the opposite of what you'd think it would. We talked about that before. All right? This is going to go up k units if k is positive, down k units if k is negative. Right? So when we look at when it's in standard form, the coordinates of the vertex are going to be h comma k. So let's do this first example, and then we'll spend next time talking about how we put things in standard form. We'll have a couple of different ways to do that. We look at this example. This is already in standard form, so let's identify the numbers. This 2 is the a. Does that matter for the vertex? No. The a, let's do the k first. Your k is going to be -2, right? Because the sign's flipped. Your h is going to be -3, because again the sign's flipped, right? It's the opposite. Okay, so the coordinates of your vertex here will be -3, -2. The important thing to remember is that you have to remember to flip the sign, essentially, what's in the inside. Okay. So we can once we have it in standard form, we can read the coordinates of the vertex right off the standard form. It was x plus 3, so the x coordinate was -3. It was a -2 on the outside, so the y coordinate's -2. So what we'll spend next time talking about is how we put these in standard form. Okay? And like I said, we'll have a couple of ways to do that, and then we'll also look at some application problems. Right? So we'll talk about that next time. Have a good one. Oh, did I give you 2? You didn't want to?